Yes? So how does it go? Does anybody need a question from last week? No? Yes?
Just like
The one?
start the lowest. You get to the just like the 6, you get to the 6.
Right, hello and welcome. The question asks you to find the shortest path, which you know how to do from year 1. Maybe it's not very safe to assume that you do know how to do that, but at least hopefully everybody remembers what the problem actually is. So the answer to the shortest path really is a set of arcs in the graph that form a path. Okay. And there was an algorithm in the first year. Dijkstra's algorithm, suppose, which has to do with labeling the vertices. However, this gives you an alternative approach, and in this approach, you want your decision variables to be, well, you want one for each of the arcs. Okay, so you'll have x for SA and x for SB and x for SC and so on. And the final one is from C to T. Okay, and they're going to be 0, 1 variables. So in some sense, it is similar to the problem of marrying people, except here it's not about marrying people. But again, you have for each edge or for each arc, you have 1, 0, 1 variable. Okay, and that's 1 if that arc is used in the shortest path, and 0 if not. Now, obviously, the objective is you want to minimize the total length of the path. So you want to minimize the sum of all the lengths of these paths. So you take minimize the sum of WE XE over all the arcs in set E. Oh, I didn't say I said minimize, but I didn't write minimize. Should have. So far everything clear? Okay. So the constraints are perhaps a bit trickier than before. But what you want is you want to leave the start, this S here, on exactly 1 arc. Okay, that's one constraint. Another one is that you want to arrive in T on exactly 1 arc. And then for all the remaining vertices, so A, B, and C, what you want is that, well, the number of arcs that you use to come there is equal to the number of arcs that you use to get out. It sounds a bit odd, perhaps, but it only means that if you get there, you want to get out as well, and if you don't get there, then you must not get out. Okay? That's kind of the condition. So if you want to leave S, that means that when you add the decision variables of all the arcs leaving S, which there are 3, you want this to be equal to 1, because you want exactly one of them to be used. You could actually, it would work even if you replace this equal to with greater than or equal to, because you could leave by 2. It wouldn't make sense. In the optimal solution, you would leave with 1 anyway, because you want to minimize the sum of the work. So it doesn't make sense to use 2. But let's put equal. Then you want to arrive, so x80 plus x bt plus x ct is 1 again. And then for every vertex other than s and t, you will have the condition that the number of incoming arcs used is equal to the number of outgoing arcs used. So you don't suddenly appear in some vertex, and you don't suddenly disappear in some vertex of ABC. Okay, so for every, so I'm going to write it for every vertex among A, B, and C. When you add all the x's such that the arc is from something. What's a good letter for something? Y. So from Y to V. Okay, so for any Y is any vertex. You add these ones. What you want is for any Y's where the arc you're using is from V to Y. Silly notation, but this is what it is. Slightly reusing letters, but it doesn't matter. They don't overlap in that code. Okay, so this is the sum of all the x's where V is at the end of them, of the arc. This is the sum of all the x's where V is at the beginning of the arc. And those two sums have to be the same. Is that clear, or is that too cryptical? Cryptical? Clear? Sleepy? No reaction. Okay, I can go home and sleep. And then, of course, for every one of these decision variables, you want this to be binary. That's the last constraint. Any questions about this formulation? You still stuck on the sums? Yeah. Oh? Did you get past that? Conceptually, it's not hard. It's just a clumsy notation. Okay, so number 2 asks you to solve this. How would you solve it? I didn't say how you should solve it, so you can solve it in any way you want. For example, by looking at all feasible solutions, or branching, or what Alicia did is put it into Mosul and gave her the answer. Can you like not do what? I'm sure you can. What was the answer? Was it this? So in the optimal solution, you'd get XSC is 1, and XCB is 1, and XBT is 1, and all the other X's. Or 0. Okay, and that gives you that path. I think that there should be a handout for you somewhere. I don't know. I think it's like 1 mark for the formulation and 1 for the solution. Okay, let's move on then to branch and bound. It's an important algorithm. Okay. I stupidly just got the idea that we could draw the feasible region. Try and draw the feasible region. You know how to. So you'll have an x1 axis and an x2 axis, and then 3 constraints as linear inequalities. Try to sketch it on your own, please. I'll try myself as well. We'll see who gets there faster.
Yeah, the last one. I think that's
The handout somewhere. So what we're Got the constraint? Did I get this right? Well, I hope it's correct. So now if we wanted to solve it, if we know what the constraints are doing, we could just look at all these integer points within the feasible region. There aren't so many, and one of them is going to be the optimal solution. But that's not what we're doing. What we're doing is we're trying to learn a more general method than just looking at the picture on this simple example. The general method is called branch and bound. And do you remember how we did the branching last week with a tree and putting zeros and ones? That sound familiar? Okay. So the idea is similar. What we're going to do is branch on the various possibilities for x1 and x2, but in a kind of a smart way. The smart way is based on solving the LP relaxation. So I'll call this problem P. No, I'll call this problem S. Sorry. I don't know why I call it S, but for some reason I call it S. Let's call it S. So do you remember I think I said last week, but the LP relaxation of S, what it is. This Z plus, that means that x1 and x2 are integer and greater than or equal to 0. Can't be negative. Okay, so that's stuff. Combined non-negativity and integrality into one constraint. So this is integer and negative. So what is the LP relaxation of this problem? Again? Yes, exactly. So if you like, you get rid of the integrality or the integer constraint, and you just solve a linear program. That's why it's called an LP relaxation. So it's to maximize the same objective function subject to the same constraints but you don't have the integer constraint. Now, the optimal solution to this, we solved it, and I'll call this R for relaxation. So the optimal solution of the relaxation is x1 equals 20 over 7, x2 is 3, and the objective is 59 over 7. Okay. So this is just an example which you can solve. Now, so I've just said why it's called LP, because it's a linear program. Why is it called a relaxation? It's like relax, take it easy. Yeah.
Because it removes the integer control.
Yes, well, kind of, yes. Because it removes a constraint also. Okay? So every time you have an optimization problem, and you have a similar problem, where there are fewer constraints. So some of the constraints of the original problem are taken away. That's called a relaxation. Maybe they're not taken away, but they're made less restrictive. That's also a relaxation. So if you have an optimization problem which has more feasible solutions, that's called feasible solutions form a superset. That's called a relaxation. Okay, because that's just the word that's used. You relax some of the constraints. So here what you relax is the integrality, you just leave it up. And as a result, something we mentioned last week as well, I think, is we can solve LPs quickly using the simplex method, for example. Much less work. You might not think so, but it's much less work than solving integer. And solving this tells us that definitely our original problem S can have a better optimal value than this number, which is just over 8. So the best solution we can hope for is that Z is going to be 8. It's certainly not going to be more than 8. Okay, one. This is less restrictive. If there was a better solution up there, that's also a solution of this. So that can't happen. Okay, so now we know that in the optimal solution of S, Z is not going to be more than 8. But we don't know what the optimal solution is yet. We got lucky, and these x's were both integer in the relaxed problem, and that would be the solution. Certainly we can't get any better. But it's not. We didn't get that. So now we'll start building the branching. The idea of the branching is the following. So at the top, we have this problem, which I call S. Now, branching, based on solving LP relaxations, tells you to solve, this one I call S1, and this one I call S2, but it's not so important. And what we're going to do, what we always do in this branching bound for the algorithm, is we do x1 less than or equal to something, and x2 is, sorry, x1 is greater than or equal to something. X2 must be the same x. This is an important mistake because it must be the same x. It's very tempting to say x1, x2, but it must be x1 both sides. Or it could be x2. However, what we do is, among the x's, we pick one that is not integer in this optimal solution of the relaxed problem. There's only one. How much is this number? Between 2 and 3? Something between 2 and 3? Yeah. So here it's between 2 and 3, but x1 can't be between 2 and 3, can it? In that problem. Because x1 has to be an integer. There's no integer between 2 and 3. So either x1 is no more than 2, and if not, then it's at least 3. Okay, so this is the branching we do. The picture. So the optimal solution we found was x2 is 3 and x1 is between 2 and 3. Okay, it's a bit of a silly example here, isn't it? Because what we're saying is that where's my green pen? Give me my green pen. Here it is. So what we're saying is either the optimal solution is to the left of here, or it's to the right of there. In this example, it looks nonsensical, but we don't know because we don't. In general, we don't have this picture, so we don't know what's there. This is the branching. Now we have a list. And on this list, we have S1 and S2. And those are the problems that we haven't solved yet. And once we've solved both S1 and S2, we will know what the optimal solution is of our thing, because we get an optimal solution of S1 and an optimal solution of S2, and look at whichever is better of the two. That would be our optimal solution. Okay, that's the same idea as last week. So if you look at this, now we go on the list and we pick one problem. So I'll pick S1 and solve S1. So the relaxation, I'll call it R1. That's the LP relaxation of S1. And it has optimal solution, which I can't remember. Which x1 is 2 and x2 is 1/2 and Z is it 15 over 2. Almost solved. But now it's starting to be interesting. You might not think so, but now it really is. Because what do we have to do? I think I usually write them. Have we found the optimum? What do we do? Branch? Say branch. Okay, what are the two branches? What are the constraints that we add? Oh, maybe I was too quick. Okay, what do we do? How do we branch? No. That's correct, but you want to use the decision variables, not the objective. Okay, you would use x2. How?
Is that equal to 0 or greater than 1?
Is that right? Either less than or well equal to 0. Well, right, less than or equal to 0, and of course it's equal to 0, or greater than or equal to 1. Why'd you say that?
Because can't be 0.5.
Yeah, because the optimum here was 1/2. So we want to split it around the 1/2. So it can't be 1/2. Either it's almost 0 or it's at least 1. Okay, so that's the same idea as before. We split it according to it. Is the idea clear? I go along. Okay, so every time we solve the relaxation of S was just this. You took away the integrality. Maybe I didn't say quite clearly what this particular problem is. You've got all those constraints up there, and you took row a little bit. All those constraints, and in addition, you have this constraint that x1 is less than or equal to 2. Okay. And with this additional constraint, the LP solution you get in simplex or so is this one. And it's still not integral, so you still don't know what the optimal solution in this branch is going to be. But then you split the problem again into two subproblems. And now I want to add them on the list. So S11 and S12, these are the problems that we haven't solved yet. Okay? Does it make any sense? Okay. And so it goes on, but now it's starting to be interesting. promise you. Before I show you how it's starting to be interesting, let's have a look at the picture again. So we were solving the problem in this left-hand part here, and we found that the optimal solution was this corner over there. Okay, so this is optimal for the relaxation of the first problem. And now what we're doing is we're splitting this problem according to being either here on this line or up here. Okay, that's what's going on. So we found this solution where x1 is 2, x2 is 1/2. And now we're kind of cutting it. The strip here in the middle gets taken out because there are no integer points in that strip. We're looking at what is the best up here and what is the best down there. Okay? These afternoons are killing me because nobody's doing it. Okay, so now I pick one subproblem from this list, and I solve the relaxation. This is how it always goes. Go on the list, pick one problem that's on the list, solve the relaxation, and see if you need to branch or not. Okay, so I randomly pick S11. Not really random because I know what I'm doing. But pick S11. Its relaxation has optimal solution, which is no. I don't know what I'm doing. One, 2 is what I want. So S11 I'm putting back on the list. S12 is the one I want to solve. So S12 quite randomly. Sorry. The optimal solution is x1 equals 2 and x2 equals 1, and the objective is 7. So here we've got this. Does the tree branch there? You see, I don't know what I'm doing. I absolutely don't know what I'm doing. So where should it be? Here. Any more errors that I need to correct? I've got the Miriam on the dice. Whatever. Pardon? No. Lost humanity. Okay, so this is it. Corrected now. Does this branch? Does the tree grow on? Why not? So what we call the thing when the tree does not branch again is called that it's pruned. And this is pruned because it's integral. So pruned by integrality. Or or optimality, if you like. Okay. Now, however, we should take note that we have a candidate for the optimal solution, haven't we? Well, we don't know. Maybe we're going to find a better one there or a better one over there. We don't know. But definitely, this is a possible optimal solution. And the possible optimal solution, the best one that we've found so far, is called the incumbent. So the incumbent is now 2 and 1, and Z is 7. X1 is 2, X2 is 1, and Z is 7. Okay. Now it's starting to be interesting. So now I pick S11 from the list. What is the best solution? Well, what is the solution of the relaxation? X1 is 3 over 2, X2 is 0, and Z is 6. Do we branch? Why not? How do you know? That's a very smart guess. Okay, say it again. Okay, the thing is, as we're going down the tree, we're adding new constraints every time. Okay? So the solution can only get worse. So we definitely can't find a solution whose objective value would be greater than 6 if we get branching. So this thing is worse than the incumbent, and that's why we proved. The idea makes sense? Yeah? It's definitely not a better solution than 6. So why do some work? That's an important idea. It's called pruned by suboptimality. Okay, I go on my list, I pick a problem on the list. There's only one, S2. Solve S2. Well, the LP relaxation of S2. Turns out that the LP relaxation of S2 is an infeasible LP. So even if I don't insist on the solutions being integers, there are no feasible solutions in that branch. Do I branch again? Or do I prune? This is called pruned by infeasibility. So I go back on my list and I pick a problem on the list. Oops, no problem on the list. What do? Problem is solved, and the current incumbent is the overall optimal solution. That's the basic idea of branching and pruning. There's one thing missing in this example, and that is if I have an incumbent already, and I find a better integer solution, I just chuck the old incumbent and replace it with the new one. And I always keep, as the incumbent, I always keep the best integer solution I found so far. Okay? And then at the end, if there are no more problems on the list, the last incumbent, if I found any, is the optimal solution. If there's still no incumbent, that means that there are no feasible solutions. Okay, so the main ideas: branching, solving LP relaxations, and then you're pruning, and you can prune for one of three reasons. You find an integer solution, if the LP relaxation is too bad, or if it's infeasible, and it's all summarized on, turn over the first page. And there's also an example there, that is the homework problem. And once you can do that, you can also do the assignment JF4, I think it is. Any questions? No? Okay, thank you. Enjoy the rest of your day.